Greetings and welcome, Internet friends. Mr. Waddy here, going to review some quadratics today. So this is the entire Chapter 8 from the what is typically called Big Ideas Algebra 1 textbook. But it also shows up in many Algebra 2 classes. And so we're going to go over this. So here we've got a classic quadratic, quite simple, nothing fancy. This was before we had any b terms showing up. And so I'll point out that b is equal to 0. It also was back when we were working with this form, essentially. I guess, yeah, I'll write that out. So we were essentially working with y equals ax squared plus c, where we used c to determine the y-intercept. And at this time, anytime b was 0, we also were able to identify that as the vertex. So the vertex and the y-intercept were one and the same in this instance. So my h comma k was 0, 0 as well. This was also when we'd first introduced the idea of slopes, and we used that term quite loosely because a parabola, its slope is always getting steeper or less steep. And so that doesn't quite make sense, but it actually helps us if we pretend just for a moment using our imagination. And so the classic slopes of a regularly shaped parabola are up 1 over 1, up 3 over 1, up 5 over 1, where the rises are the consecutive odd numbers, 1, 3, 5, 7, 9, etc. And then what I do is I multiply those rises by whatever my a value is. And so I'm going to multiply them by a half. And I'm intentionally going to not simplify this very much. So the numerator is, I'm going to go up a half over 1, up 3 halves over 1, up 5 halves over 1 as my rises. Now, one of the things we've also done is whenever I have an a value in a denominator that isn't 1, changing the y scale to count by that value. So notice here I'm actually counting by halves. Oh, and thanks, Past Waddy. Looks like you've already set this scale up successfully. And so now that I'm counting by halves, I'm going to go up a half and over 1. Notice my x scale is counting by ones, my y scale is counting by halves. Up 3 halves over 1, plot a point, and up 5 halves over 1. And then we also had discovered that the axis of symmetry is always the equation x equals the x coordinate of the vertex, that parabolas are able to be viewed as kind of a mirror image of themselves over that axis of symmetry. And so I can actually, since this point it was 1 away, then 1 away over here, 2 away from the line, 2 over here, 3 away from the line, 3 away over here, gives me my points. And so this is plenty of points to draw my parabola. Remember that the parabola does not come to a sharp point or cusp at the bottom. It's a smooth transition. But your ability to draw these will not be what I grade it based on. I'm more interested in the points you make and the work you do to justify it. All right, so here's a parabola. Let's identify the characteristics. And so this one, I would say, opens up, as indicated by the smile that it's giving us. In fact, you can actually kind of determine what the a value is. The time it takes to go over 1, it's actually going up 2 over 1, and then it'll go up 6 over 1 from there. So it looks like it was a vert stretch. So it's not a regularly shaped parabola. The y-intercept is occurring at -1. And the vertex, we can read that point right here, is 1, -3 over 1 down 3 for the vertex. And let's get that axis of symmetry as well. The AOS is going to be x equals 1, and remember that's always just the x coordinate of the vertex. And x equals a number will always give you the equation of a vertical line. So the axis of symmetry will never just be the number 1. It's x equals 1. So it represents all points whose x coordinates are 1. All right, so there's, I think I've got everything there, right? Yeah, bop, 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 bop. Yeah, looks like everything important, all of those qualities. Okay, here we go. Here's another one. Let's, a is equal to -2. C is equal to 6. There's no b term, so my y int is -6, like so. My slopes will be -2 times 1 over 1, -2 times 3 over 1, -2 times 5 over 1, and so down 2 over 1, down 6 over 1, down 10 over 1. And so since this y-intercept is also my vertex because there was no b term, I just go, yeah, down 2 over 1, down 1, 2, 3, 4, 5, 6 over 1. And let's mirror those points as well and draw my parabola. Good enough, good enough. Let's see, compare to the graph of x squared. And so based on the a value, it was, it's negative, so it opens down. Since 2 is beyond -1 or 1, it's a vertical stretch by 2. And the y-intercept was 6, so it was a vertical, it was shifted down 6 units. And so that's how we compare it to the parent function. The parent function would have been a vertex at 0, 0, and then the classic slopes of up 1 over 1, up 3 over 1. And so we're describing, right, how did that compare to that? Compare to the graph of the parent function. We also, you could say, like, you know, describe the function in terms of transformations as far as that goes. All right, here we go. A equals a half. Now, unfortunately, I'd given myself most of all of the fraction problems. I figured those were going to be the ones that would screw you up the most. So I've got my A, B, and C. This is in standard form, and that's the least helpful form that we could have. But it's kind of a classic form. It still shows up quite a bit. So y equals ax squared plus bx plus c is what we are describing. And so the y-intercept, which is now not the vertex, is at 10, and that's not even on my grid. That's interesting, isn't it? As far as the vertex goes, I was calling these v sub x for a bit. I'm going to try to get back into the habit of calling them h. I could calculate the x coordinate of the vertex by using the formula -b over 2a. Let's see. So working over here, I'm just sliding things over. So the opposite of -6 over 2 times a half is going to be 6 over 1. So h equals 6 is what I would end up getting. And so I know that 6 is where the x coordinate is. To find the y coordinate k, we have to use the actual equation and plug 6 in is what we end up doing. So I'm going to take this and 1/2 x squared minus 6x plus 10, and everywhere there was an x, there is now going to be a 6. Let's see, and now I just got anxiety. Is my calculator close by? All right, phew, there it is. Okay, and so I just PEMDAS. 6 squared is 36. It doesn't look like I'll need my calculator, but now, am I getting too confident, overconfident? Am I going to make a mistake? 36 divided by 2 is 18 minus 36 plus 10 equals 18 minus 36. -18 plus 10 is -8. You might hear my kids talking in the background this morning. We're all hanging out, quarantine, sort of thing like that. Self-quarantine, social distancing. But don't worry, math is still true, and I'm still here for you, teaching you the algebra. Let's see. So 6, -8, right there is my vertex. I've got to figure out some slopes, because that y-intercept is actually way off my grid that I gave you. So for slopes, I'll have the a half times 1 over 1, a half times 3 over 1, and a half times 5 over 1, resulting in up, oh, look at that y scale, it's already counting by a half, so up a half over 1, up 3 halves over 1, up 1, 2, 3, 4, 5 halves over 1, and actually it looks like I've got enough space I could do the up 7, 1, 2, 3, 4, 5, 6, 7 halves over 1, and then I can mirror these over the axis of symmetry. Now this problem did ask us about domain and range. Remember that domain are the possible x values, and every parabola that is opening up or down has a domain from which are all real numbers, all reals. Because even though this parabola is getting super steep, it still goes all the way to the left, negative infinity, and all the way to the right, positive infinity. It exists all there. But the range, because this has a minimum value, it only exists above or at that point. And so the range are going to be all y values greater than or equal to -8 in this case. That's the lowest point. And then all the y values above that exist. Did we hit everything? Yeah, axis of symmetry would have been x equals 6, right? The x coordinate of the vertex. Yeah, I think we did everything we need to for that. Let's keep cruising. Here we go. Here's the most powerful form. Y equals a parentheses x minus h squared plus k. Vertex form, where a is the right shape slopes of the parabola, h and k is the vertex. And the beautiful thing about this is, just like slope-intercept form with equations of lines, by merely looking at the equation, I can determine all of the most important things that I need. So h is a -4. Careful, it's always the opposite of the number with the x, and k is the +7. And so my vertex, I guess it's not as much like slope-intercept form as it is point-slope form, if you think about it. So -4, up 7, right there. And then a is -1. The slopes are down 1 over 1, down 3 over 1, down 5 over 1. I'm going through these a lot quicker in my explanations because theoretically you've already practiced a whole bunch of these. You've watched the much longer videos on these topics, and so I'm just doing a fast review. Compared to the graph, it was a vert flip, right, because of the negative. No stretch because it was exactly 1, so it was a regular shape. And then as far as it was shifted left 4, right, left 4, and then up 7. Boom. There we go. So good. Keep on cruising. All right, write a quadratic function. Good thing. They gave us the vertex. So here is hk, and then they gave me a particular point, x1, y1 is what I'll consider that. And so when writing the equation of a quadratic function, given a particular set of information, if one of those pieces of information is my vertex, then I should use vertex form. If they gave me intercepts, then I should use the intercepts form, right? And so I'm going to do the classic algebra move of plugging in what I know and solving for what I don't. Right now I don't know what a is. So I'm plugging in 7 and 4 for y and x. I'm plugging in h and k for h and k, right? Let's see. I don't know. I was trying to do the color thing, but then I gave up a bit. 7 equals a times 4 minus 3 is 1 squared plus 2. 7 equals 1 squared is 1, so 1a plus 2. Subtract 2 from both sides, and I get a equals 5. And so now that I have a, h, and k, I can write my equation y equals 5 parentheses x minus 3 all squared plus 2 is the equation of the parabola. And now using that, I could make predictions, like how high might the object be if y represented the height, given a time x, right? I could plug in when x is 10, what is y, sort of thing. I can do all sorts of great stuff. And so, so this is kind of how you can calculate this based off of a couple of data values is what we end up doing here. Here we go. Quadratic, graph the quadratic. This is currently an intercepts form. So y equals a parentheses x minus p times x minus q is intercepts form, where p and q represent the x-intercepts. And so for this particular one, the a is the -3, and then p is -3, q is -1. Notice these also do kind of the opposites thing that we've had previously. And so I've got one x-intercept at -3, 0, one at -1, 0. Interesting. Now, I can do my slopes move, and I'm going to be going down 3 over 1, down 9 over 1, down 15 over 1. If I take 1, 3, 5, multiply by those. And so I know it's an upside down parabola, right? It's gonna look something like that. And you might be able to guess, because these are only 2 units apart, that, oh, it must mean that the vertex is up here in order to go down 3 over 1 to both of those. And I'm fine if you use that sort of intuition. However, there was a little formula that we could use to calculate h, which was taking the p and q, add them together, and divide by 2. And essentially, you can do that with any 2 points on a parabola that have the same y-intercept. Both of these have a y-coordinate, of 0, because any 2 points on a parabola that have the same height will be the same distance from one another. And so if I midpoint, that's always going to give me the h value. And so I could have done -3 minus 1 divided by 2, which is, right, -4 divided by 2, which is -2, is what I end up getting for h. And so that's predictable. And then if I wanted, I could have plugged this in. And I guess I'm here, so I might as well. And so I would have had -3 times -2 plus 3 and a -2 plus 1. And so I'm plugging this in right here, -2 for both of the x's, and that's going to calculate the value of k for me. So -3 times 1 times -1, so this is +3 is the value of k. And so -2, 3, kind of where I predicted. So if you know your slopes, you might be able to predict these things. If the intercepts, though, were like 5 units apart, yeah, you're going to have a little bit of a harder time. So down 3 over 1, and then down 9, which is way off page. And so all I know is that, yeah, by the time this leaves this window, it hasn't yet reached another over 1. Okay, whew. Use the zeros to graph the function. So this was from 8.5, also talking about intercepts form. And so the idea is, what if I could write this in intercepts form, x minus p, x minus q, which just basically means factor it. Now, zeros are, what are the x values that give me a 0 for y? And so I'm going to, well, actually, I don't even have to. Let me just write this out. If I was calculating the zeros, I would plug in 0 for y, solve for x. And in this case, at this time, the only way we know how to solve for x in a quadratic is by factoring. In a couple chapters, we'll be doing different stuff, solving for non-factorable problems. But here we go. I can factor this. First thing I'm going to do is a GCF. That looks like a great idea to me. So -2 times, and what would be left would be x squared minus 3x, and minus 4. And this whole thing is still equal to y. I'm just putting it in this form, and then I'll read the intercepts right off of it. There were some problems where they asked you to plug in 0 for y, or to find, if they ask you to find the zeros, that's when you plug in 0 for y and solve. But it's essentially accomplishing the same thing. Now, what's left in here is factorable. The leading coefficient is 1, so I don't have to do AC. Find the factors of C that subtract to B, and so that's 1 and 4. And so I'll have -2, x with a 1, x with a 4, y equals... they multiply to be negative, so their signs are different. They add to be a negative, and so the larger of the two numbers must have been the negative. So here is Intercepts Form converted out of standard form. And as far as zeros go, there was a cool little fact that as long as the x terms in these factors have a 1 for their values, all you have to do is opposite the number with them. So the zeros would be -1 and 4, and so I got -1 and 4 as my zeros. And now here's where, man, let's see, 1, 1, 2, I don't know how to count. That's an odd number of units away from each other. So my, let's do it. H, it's going to be an odd number. That's okay. -1 plus 4 divided by 2 is 3/2, which is 1.5. And so my axis of symmetry and the x-coordinate of my vertex is going to be here. Now, based on the a value, the -2, I know it's upside down parabola. So it's going to be something like this. If you're clever, maybe you could figure out a way to find k, through intuition. Let's see, how much space do I have? I don't have a lot. I'm almost done. Let's find k. We'll plug in 1.5, and I could plug it in this form or this form. This one looks easier to me right now. -2 times 1.5 plus 1 times 1.5 minus 4. And so -2 times 2.5, and this one's going to be what, negative 2.5? Now 2.5 squared, isn't that 6.25? All right. And that's negative, multiply that by 2. I'm getting k equals 12.5. Let's see, my sky blue. Got to have my sky blue. So 12.5 for k, and so over 2, up 12. Oh, and these are counting by 2s. Quiet, kids, quiet. And so 12.5, it's not very high is the point. And all right, let's figure out some slopes real quick. -2. So from 12.5 down 2 brings me to 10.5 over 1 right here. And then down 3 would bring me to 7.5 over 1 right here. And so it's something like this. You got to be quiet, kiddos. Daddy's almost done. All right, so something like this, something like this. That's a sad looking arrow, but that's good enough. All right, so bunch of different ways we have to interact with these parabolas depending on the forms that we take. All right, as far as calculating given a data set, graphing those things is a good idea. We talked about how to use technology in order to get a regression equation, a best fit curve. That's a possibility as well. I plotted this in Desmos, but since this is like a falling object, I actually know what my vertex is. Since it was dropped and not thrown, my vertex is going to be this value right here. And so my vertex is 0, 150. And then, if I want to find the equation, I can take either of these points. Let's take, this one seems to have small-ish numbers. And so here's 2, 86. And I could have taken either of these points, but I'll use this point as my x1, y1, and oh, I know the vertex, so I should use vertex form. So y equals a abs. I almost got through the whole video without saying absolute value when I wasn't supposed to. Y equals a parentheses x minus h squared plus k. And so let's see, plug in 86 for a y value, that works. And the corresponding x value that works with that is the following. And then I'll plug in h and k. And so minus 0 and plus 150. And now I solve for a. 86 equals a times 2 squared plus 150 equals 4a plus 150. I realize this is a longer video, but it's review, and I wanted to give you as many of each kind of example as possible. All right, I'm not doing 86 minus 150 in my head right now. It's too risky, too risky. Negative 64 equals 4a. Divide both sides by 4, and I end up getting a equals negative 16. Oh, which actually, on the planet Earth, negative 16 feet per second squared is the acceleration due to gravity. And so if you didn't know that, this is actually one of the ways you could have discovered the way gravity behaves on our planet. And so hey, that's pretty great. So here we go. Let's see. What did they want to do? Write a function that models the data. And so my function is y equals negative 16 x minus 0 squared plus 150. I guess I could write that in this form, negative 16 x squared plus 150, either of those. And then did they ask us how long is the object in the air? That's asking the question, kind of when does it land, right? What number of seconds does it take to land? Well, that's going to occur whenever y is 0. And so let's do that over here. 0 equals negative... I wonder, did they want us to use technology for this one? I'm trying not to... if I plug in 0, this problem isn't quite factorable. And so it's... I haven't shown you how to solve these yet. So let's say I did it... Well, I'll tell you what. Foreshadowing. 0 equals negative 16x squared. We'll have a future lesson on this. Yeah, normally you would try to factor it. This isn't quite factorable. It's going to be decimals, essentially. And so I would subtract 150 from both sides. I'm all out of room on my page. So I'm just going to write negative 150 equals negative 16x squared. Then I would have divided both sides by negative 16. And I get 9.375. And then this is the one part you don't know how to do yet. You can root both sides, and technically you get two answers. Square root, I get 3.06. Plus or minus, technically, 3.062. Now, theoretically, if you had graphed this with technology, you would have clicked on the point and figured out exactly where it landed. So 3.062 seconds is how long it's in the air. The minus answer exists algebraically, but we exclude it in terms of the real-world problem because we don't know what negative 3.6 seconds would mean. All right. Whew. Well, I hope you all had a great time reviewing with me, getting ready for your upcoming test, and you all have a great day. Take care.